Okay. So last time we were looking at the Klein-Gordon equation, and we of course started off by calling it the Schrodinger-Klein-Gordon equation for historical reasons. But from now on, we'll just call it the Klein-Gordon equation. And this equation is basically something we had written down, a box, del mu, maybe I'll just go back and show that box acting plus mc upon h bar whole squared on psi equals 0. And as I said, this quantity was the inverse Compton wavelength squared. Okay. So what we are going to do today is basically study this equation in a little better fashion. Well, I don't know whether better fashion, but in a little different way than one usually studies this equation. And that is to study it in a two-component formulation. Okay, so remember that that box contains derivative of psi with respect to time twice. Okay, so it's a second order derivative with respect to time as well as with space. But we are kind of used to having second spatial derivative. Even the non-relativistic Schrodinger equation had grad square acting on psi, but it was only I h bar del psi by del t. So what we'll try to do here is to write down two new components, eta and chi, and they are linear combination of psi and its time derivative. Okay, so and these are the two linear combinations. One is psi plus the time derivative, and the other one is psi minus the time derivative. Okay, so now clearly, if you are looking at a free particle at rest, then I h bar del psi by del t would just give you the answer E, and this factor is going to be, this entire quantity is going to be psi plus E times psi divided by mc squared, and this quantity will be psi minus E times psi divided by mc squared. Okay, so therefore if E is equal to mc squared, that is the case when the particle is free and is at rest, then in that case this quantity will add up and you will get because E by mc squared is just 1, and it will give you eta is equal to psi, and this term would just cancel out. Okay, so this is what we would call a particle like state. So eta describes particle state. On the other hand, if you have E equals minus mc squared, that is what we would have called antiparticle state. In that case, it is a chi which is non-zero and eta is 0. Okay, when you substitute E is equal to minus mc squared. Okay, but remember that all this is done when both particle and antiparticle are at rest. Okay, so the choice of these two variables is basically based on this fact that in when you are at rest, then only one of the component is non-zero, the other component is just 0. Okay, fine. So what we'll do is we'll just rewrite the Klein-Gordon equation in terms of eta and chi. Okay, so here's the form. So what we'll do is that we'll just first take the derivatives of these quantities, and then we kind of start identifying where the derivatives would belong to. Okay, so let's take I h bar del psi del eta by del t. If you do that, just take the first expression. It is a bit too high, unfortunately. So you just have to write down a psi dot and a psi double dot piece, which is what I'm writing here, with the I h bar sitting outside. Okay, but you can check that if you look at I h bar by mc squared psi dot, then that term, which is written out here, okay, this can be obtained by just taking eta minus chi, because in that case psi would cancel out, and up to some factor, uh, this quantity is related to eta minus chi. Okay, so the factor is basically mc squared. So I h bar upon mc squared d psi by dt is just eta minus chi. So at this place we could just substitute eta minus chi to write down this expression. You can do the similar thing for psi double dot, for which we just go back all the way to the Klein-Gordon equation, which in the non-covariant form would look like this. Okay, so what we can do is we can take psi double dot and replace that by this expression. Okay, and of course at this place, remember, there's a spatial derivative acting on it, but eta and chi are defined in such a way that they don't involve space derivative at all. So what we will do is we will substitute psi, which is chi plus eta. Okay, if you take chi plus eta, these terms cancel and the psi would add up. Okay, so wherever we get psi without time derivative, we would replace that by eta plus chi. Okay, so if you do that, then you can check that the entire equation would take the form I h bar del eta by del t is equal to minus h bar squared upon 2m nabla square acting on eta plus chi plus mc squared times eta. And you can do the same stuff, although I have not written it out here, but you could kind of just go back and take I h bar del chi by del t and carry out the same computation. You get a del psi by del t here, write that in terms of eta minus chi, and del psi by del t, del squared psi by del t squared here, use the Klein-Gordon equation. And if you do that, you get the equation which takes this form. Notice that this is minus h bar squared by 2m, whereas this is plus h bar squared by 2m. Okay. And this is a plus mc squared eta term, and this is a minus mc squared eta term. Okay. Now, it should not come as a surprise here that if you say that if the particle carries no momentum, okay, then of course the grad square acting on this entire piece would give you answer 0. Okay, and in that case the equations actually decouple. Okay, because if this gives you 0, then eta dot is related to eta and chi dot is related to chi. The reason why it shouldn't come as a surprise is because we had seen that if the particle is at rest, these pieces are just popping out, with the other fellow being just 0. Okay, so clearly if E is equal to mc squared, you would get eta dot to be related to mc squared eta. But if E is equal to minus mc squared, then it is this term which will show up. Okay, so the fact that this equation factorizes uh, in the zero momentum limit is something we knew even earlier. Okay, so but notice one more thing, that this equation look pretty much like the Schrodinger equation. Okay, because minus h bar square upon 2m grad square acting on something or other. Okay, plus this piece, but that is more like a constant piece. So therefore, in when you think about Schrodinger equation, adding a constant to the potential just shifts the entire spectrum by that factor. Okay, so in that sense, it doesn't really uh, make any difference in terms of physics of the system, because remember in quantum mechanics, you really do not measure absolute energies. All you measure is relative energies. For example, in hydrogen atom, uh, if you want to find the energy spectrum, you can of course solve the Schrodinger equation. But if you want to determine experimentally, then what you do is basically excite an electron from a particular state to some other state, and then when it decays, it emits light. And that light is actually just the difference between the energies of the two states. Okay, so you can of course add a constant to both these energies and it wouldn't matter at all. In fact, not just in quantum mechanics, even in quantum field theory, it wouldn't matter at all. Only place where this absolute uh, zero point, what we would call a 0 point energy, would become important when you study theories which involves dynamical gravity. Okay, so until you really ask questions related to um, say related to quantum gravity, you really need not worry about a constant shift of the entire spectrum. So from that point of view, we could have said that, like, okay, we can just forget about this, and this pretty much looks like a Schrodinger equation, except that, like, it's not exactly the Schrodinger equation because you have a eta here and a eta plus chi there. Okay, fine. Now, the main difference, of course, between the Schrodinger equation, which I mentioned, is that you don't have the equation as it is. You have some admixture of the other component, and that is just as well. In fact, that is the reason, that is the kind of effect due to relativity, that you would see the other component contributing to the dynamics of I mean, the positive energy component would have a contribution from negative energy and vice versa. Okay. So what we can try to do is that we can take these two equations and try to write them in a matrix form. Okay. So to do that, we kind of think of eta and chi forming a column vector. Okay. And if you make that as a column vector, then this I bar del t acting on eta chi as a column vector is a kind of trivial thing to write. The right hand side, we will have to look at this expression, and we notice that this particular piece has a plus minus sign. Okay. Whereas this piece is a bit complicated because it involves both eta and chi. So therefore, a matrix sitting around here should have both components of the column vector contributing at both places. So therefore, what you get is an expression which is like this. The matrix, the 2 by 2 matrix here is 1, 1, minus 1, minus 1. That is simply because this, remember I'm writing minus h bar squared by 2m outside. So therefore, this quantity is 1, 1. Whereas if I pull minus h bar square outside, then this quantity is minus 1, minus 1. Okay. So that is how this expression comes about, with a grad square acting on eta and chi. Okay. And MC squared piece has is diagonal but has a relative sign. Okay, so it comes about in this particular fashion. Okay. So of course, I mean, you don't have to write it in a matrix form to realize that the equations are not decoupled. We of course could see it right here also, that eta equation has a chi and vice versa. Okay. But what we could do is that at least writing in the matrix form kind of makes you think that, like, okay, you can try diagonalizing these matrices. Okay. So, so that is the thing that we are going to do next. Okay. And as I mentioned some time ago, that of course they trivially decouple when grad square acting on eta is 0. Okay. In that case, we knew that in the rest frame, the two particle antiparticle degrees of freedom completely decouple. Okay. So does that sound okay?
So one thing,
Yeah.
hello. Yeah, one thing I wanted to know, if you go back 2 slides up, where you have written that for the antiparticle it is E equal minus mc square
Yeah.
at rest. So naively speaking, it still looks like it has negative kinetic energy or something like negative rest mass or something.
Yeah.
But it does not, right?
Yeah, it does not. But there are two solutions corresponding to the energy, which is a plus minus square root values. Okay.
Yes.
But absolute energy is still just the MC squared factor. Okay.
Is it just that it enters the equation this way, but actual energy is still positive?
Exactly. Because what you really need is the gap between the two energy states, right? So if you create a negative energy, the quote unquote negative energy state, you basically have to kind of, I mean, you create a pair, and that pair requires twice as much the total energy. Okay.
Okay. Okay.
So, so it's, yeah. So this is how it enters the equation, but in reality, you really need uh, the positive energy to be pumped in to produce the particle.
Actual eigenvalue is E square, right?
Actual eigenvalue is E squared, exactly. Yeah. Okay. Any
Sir,
other question? Yes.
so in the race frame of the particle, if we treat the momentum as zero, then I mean those Heisenberg uncertainties are those satisfied?
What Heisenberg? No. Okay, I understand what you're saying. That whether I said P equals to equal to 0 or this thing, right? I mean, you're saying that, like, how can I keep P exactly equal to 0?
Yes.
Well, that is not the problem. I mean, we are not trying to kind of do a measurement here, right? If you're trying to do a measurement and trying to find where the particle is, then you could get into the issue. This is just a statement about if the particle is at rest. Okay, how would the uh, how would the equation look like? Okay,
No, even
you
there
know,
is another problem. If we treat that del square of eta is zero, say in one dimension, then eta will be a form of a plus bx, and that won't remain. I mean, the norm will not be. I mean, finite actually.
yeah, but like, yeah, I understand, but that is not the question that we are worried about right now. Okay, what we are worried about is whether the equation is decoupling or not. And in reality, what happens is that like you are not really looking at objects whose momentum is exactly zero. Okay, there is always a quantum fluctuation for the particle, but that is not my concern right now. I mean, we are going to look for solutions which are like wave packets anyway. Okay, but
Oh,
but the argument that I'm trying to give is that if you look at zero momentum states, okay, which of course have extended wave, very long wavelength. So these are like very large extended particles in some sense, okay, but which is fine. That is not a problem. Okay, uh, it's like even in the plane wave case, if you take p1 to 0 limit, okay, that wave has a very long wavelength. Okay, uh, which is fine. I think it's not a problem. Okay, and it is
fine.
consistent with the uncertainty principle. It is not that like that kind of wave is going to be detectable, or is that kind of wave is something we are interested in, unless it kind of contributes some non-trivial physics. Uh, it is not going to be important for us. Okay, so it's not like one is trying to exactly set this quantity to zero, but we're trying to say that like if it is zero, then the equation decouples. Any other question? Okay. So what we want to do is to try diagonalizing these two matrices, this 1, 1, -1, -1 matrix. Okay. And while diagonalizing this, we have to ensure that this doesn't become off diagonal. Okay. So in that sense, you have to find a coordinate system in which uh, both the matrices remain diagonal. Okay. Now, this matrix 1, 1, -1, -1 can be written in terms of Pauli matrices. And you can easily see that like 1, -1 diagonally is just sigma 3. And 1, -1 off diagonally is just I times sigma 2. Okay. Of course, this is sigma 3. And that's kind of trivial. Okay. So, uh, so notice that therefore this equation contains only sigma 3 and sigma 2. Okay. So if you try to kind of think of sigma 3 and sigma 2 defining some space, some auxiliary space, okay, then this object, the right hand side of the matrix equation, is some kind of a vector in that two-dimensional auxiliary space. Okay, uh, one direction in that two dimension, one direction is parameterized by sigma 3, the other direction is parameterized by sigma 2, to be precise I times sigma 2. But let's take it as sigma 3 and sigma 2 just for the argument's sake. Okay, so and we want to find out what is the direction in which this right hand side of this equation, okay, is pointing to. Okay, so if you kind of rotate the basis of sigma 3 and I sigma 2 in such a way that in the new basis, one of the basis vector is pointing exactly in this direction, okay, then we have diagonalized the equation. Okay, that is what we want to do. Is that clear? Hello? Hello?
Yes, sir.
Is that clear?
Yeah.
Okay. So, but now clearly, if you have something something defined in terms of sigma 3 and sigma 2, okay, then imagine sigma 3 and sigma 2 is like coordinates z and y. Okay, then if you want to rotate the z and y plane such that you kind of point one of the axis along the desired direction inside the z and y plane, then you would want to do the rotation about x-axis, right? Because it's like if you want to do a rotation in xy plane, you do a rotation about the rotation of xy plane, you do a rotation about z axis, right? So what we will do here is that we will do a rotation in sigma 1 direction. Okay, so if you do a rotation in sigma 1 direction, then sigma 3 and sigma 2 will mix. Okay, and this will help us diagonalize the entire equation. Okay, fine. So so to do that, let's collect the terms which involve sigma 3 and sigma 2. And so it's the same equation, but now written in terms of sigma 3 and sigma 2 instead of those 2 by 2 matrices. So left hand side is unaffected. Right hand side, sigma 3 has a term which is minus x bar square upon 2m times grad square plus mc squared uh, times, of course, our favorite two component vector, and I times sigma 2 times this quantity. Okay, that is where the I times sigma 2 kind of factor gets in. Okay, so this is how this equation is going to look like. Okay, so what we want to do is to basically do a rotation about the quote unquote sigma 1 direction. Uh, so of course, when you do a rotation about sigma 1 direction, then your rotation matrix should contain sigma 1 in it in some sense. Okay, so such that we get this stuff diagonalized. Okay, now in fact the way to do this is best described by kind of drawing a picture, this thing, and I haven't done that again, unfortunately. uh, it is, the diagram it is taking a bit longer. Maybe what I'll do next time is just draw it by hand and take a snapshot and kind of paste it in the file. Okay, that would be probably a faster thing to do. Okay, but uh, but just for simplicity, just to understand how to do this computation, let's assume that we can do a decomposition of these two component vector in terms of plane wave. Use a plane wave basis for describing this. After all, we are looking at free particle in the spatial direction. Let's not worry about how it looks like in the time direction, but in space direction, we just choose that to be a plane wave. If you do that, then minus h bar squared nabla squared can be replaced by p squared. Okay, and this equation just takes a form like that. Okay, fine. So what we will do now is take the right hand side of this piece and try to diagonalize it. Now notice one thing, that that this, although this piece is multiplied by sigma 3, this piece is not multiplied by sigma 2, but it's multiplied by I times sigma 2. Okay, and now you know that the Pauli matrix is square to 1. Okay, like sigma 3 square is 1, sigma 2 square is also 1. But what we have is not sigma 3 and sigma 2, but what we have is sigma 3 and I times sigma 2. Okay, so therefore if you think of these as basis vectors, then sigma 3 squares to 1, but I sigma 2 squares to minus 1. Okay, and in that sense, in this auxiliary space, we actually have a Lorentzian signature. Okay, is that fine? So we are looking at a space where one direction, which is given by a unit vector sigma 3, has a norm which is positive, and the other direction, which is kind of for which the unit vector is I times sigma 2, has negative norm. Okay, fine. So this has a kind of Lorentzian signature. Fine.
Sir,
Yeah.
so when we define those momentum operators in non-relativistic case, we use things like Hermitian operators to define them, and those were because things are normalizable. And
Yeah.
now in relativistic case, when things are not normalizable, can we still define p cap as minus I h cut grad?
Yeah. I don't see why these two things are related. I mean, free particle state is not normalizable even in non-relativistic quantum mechanics. No, we had to do box normalization. The plane wave is not normalizable, but that did not stop us from kind of replacing p by minus I h bar del x.
Okay.
Okay. Okay. So any questions about this thing? So this right hand side is basically described in terms of some auxiliary Lorentzian space in which sigma 3 and I sigma 2 are basis vectors. Okay, and we want to do a rotation, as I said right in the beginning, to kind of uh, change the um, coordinates in such a way that one of the coordinate points in the direction in which this vector is pointing. Okay, but given that this has a Lorentzian signature, if the rotation in the Lorentzian space is actually what we should have called Lorentz boost. Okay, so what we should be doing is really Lorentz boost. Okay, so in that case, the diagonalizing rotation that we want to do is cannot be a trigonometric angle, but it has to be a hyperbolic angle. Is it okay? So it's exactly the way Lorentz boosts were written in terms of cos, hyperbolic, sine, hyperbolic, whereas rotations were written in terms of cos and sine. Okay, in this particular case, what we need to do is a hyperbolic transformation. Okay, so let's try to find out what that transformation is. Okay, so suppose we define a new basis in which this equation becomes diagonal. Okay, and let's consider that transformation is e to the I times s acting on this eta chi. Then you can check that if s is minus I by 2 times sigma 1, I would written it in a matrix form, but this is just the sigma 1 matrix, which is what we knew right in the beginning, that we need to do a rotation about the sigma 1 direction to diagonalize this expression. So, so s is minus I by 2 times sigma 1 times tan hyperbolic inverse of this particular quantity, p squared upon 2m upon mc squared plus p squared upon 2m. Okay. So if you take this expression, like notice that these two pieces are exactly these pieces sitting in here, p squared upon 2m and p squared upon 2m plus mc squared. Okay. So we are looking at tan hyperbolic inverse of those two pieces. Okay. So if you do this transformation, then the new eta and chi that you will get would have the equation completely diagonal in terms of eta and chi. Okay, so eta tilde and chi tilde are basically decoupled degrees of freedom uh, when uh, when original eta and chi, which we would have called particle and antiparticle degrees of freedom, were not completely decoupled for a general equation. Okay, fine. So we want to determine the hyperbolic angle theta, uh, uh, and that we can do by just using geometric technique. Of course, it's kind of algebraically it's kind of easy. All you have to do is to say theta is equal to tan hyperbolic inverse times this entire object, p squared upon 2m divided by mc squared plus p squared upon 2m. And so tan hyperbolic of theta is going to be this expression. Okay. So, so let's try to kind of understand how we go about this thing. So, as I said, let's imagine sigma 3 to be space-like direction and I sigma 2 to be some time-like direction in a two-dimensional Lorentzian space. Okay, and they define some unit vectors in orthogonal direction. Okay, then in that case, this equation 7, as I said, can be interpreted as a vector in the two-dimensional Lorentzian space. Okay. Okay, so now let's go back to this equation again. So, so this is like is to be written as vector. This is like x times I hat plus. Hello, am I audible?
Yes,
Yes,
sir.
you are.
Yeah. Okay. Okay, because in between it just said that my internet connection is unstable, so I was not sure. Okay, so coming back to this, I was saying that, like, if you are looking at a two-dimensional vector, you write down that vector as x times I hat plus y times j hat, right? So sigma 3 and I sigma 2 are like analogs of I hat and j hat, and p squared upon 2m plus mc squared and p squared upon 2m are analogs of x and y. Okay, so you have a vector and you want to ask what is its x direction projection and y direction projection. And what I'm going to say is that if you look at that as a vector, then sigma 3 component of that vector has length mc squared plus p squared upon 2m, because that is the factor which is sitting around here. Okay, so this is the sigma 3 projection, and sigma 2 projection, of course, no points for guessing that, is going to be p squared upon 2m. Okay, fine. So, so these are two kind of orthogonal directions. So it is like one goes this way, the other goes that way. And since you have both components, your vector is kind of pointing something like at some angle, okay, which has some sigma I sigma 2 component and some sigma 3 component. Okay, that is how it is going to look like. Okay, so we want to ask what is the length of the vector which one is trying to look at, whose component projections are given out here. Okay, which is mc squared plus p squared by 2m and p squared by 2m. And you can check this kind of straightforward calculation, that the length of that vector is actually square root of m squared c to the 4 plus p squared c squared. Okay, now you would say, like, what's the big deal? This is what we would have expected anyway. Okay, and of course there is no big deal. Uh, After all, that is the energy eigenvalue that you want, and this equation is just IH bar del T would have given you energy. So right hand side better give you square root of m squared c to the 4 plus p squared c squared. Okay. The only thing is that, like, we looked at it more like a vector in two-dimensional space, and with these kind of projections, and we find that we can determine the theta angle subtended by this vector with respect to, say, sigma 3 axis is given by this factor. Okay, fine.
Sir,
Yes,
so here the magnitude is found by doing square of the time minus
exactly.
square of the so
Yes, yes, it's a Lorentzian signature, no? So you take mc squared plus p
okay.
squared upon 2m whole squared minus p squared upon 2m whole squared. And you can check that you will get that answer is p squared c squared plus m squared c to the 4. It is just, 2-3 line computation. Okay, is that fine?
Yes.
Okay. So, yeah, so therefore, if you choose this transformation, then your equation is diagonalized, and we have chosen that diagonalization direction to be sigma 3. Okay, and if you do that, then your equation just takes this form. Okay, now it is sigma 3 which tells you that the eta tilde is a positive energy solution and chi tilde is a negative energy solution. Okay, because sigma 3 has diagonally 1 minus 1 factor. Okay, so at rest, eta and chi were positive and negative energy solutions, but for arbitrary momentum, eta tilde and chi tilde are the correct uh, positive and negative energy solutions. And remember that eta tilde and chi tilde are not defined once and for all momenta, because the transformation which takes you from eta and chi to eta tilde and chi tilde itself depends on momentum. Okay, so the theta angle that you need to choose for decoupling these modes itself depends on what p value that you are looking at. Okay, but that is okay. I mean, that is the kind of thing that one does when one does Bogoliubov transformation also, say when you are trying to study something like superconductivity, where you want to kind of look at finite temperature Fermi surface and rewrite in terms of new quasi particles, and in that case also, as the system has a different temperature, particles carry different kinds of momenta, you need to do a transformation which depends on both temperature and the momentum of the particle. Okay, to write down a correct set of quasi particles. Okay, this is very much like that, although we are doing entire computation at essentially at zero temperature. Okay, so therefore this expression is only momentum dependent and does not depend on any other quantities. Okay, fine.
So
Yeah, yes,
in original Klein-Gordon equation, we
yeah.
had psi as a scale, right?
Psi as a scalar.
Like it didn't transform under Lorentz transformation. Psi itself didn't transform.
Yes,
Now, then in order to write it in terms of two components, eta and chi, we defined eta and chi in some particular fashion.
that is right. Yeah,
Psi minus iota
yeah,
h by mc squared del by del t and
yeah,
plus.
like that. Yeah,
So here, psi and chi do not seem to be scalars as such. They will transform because there's a del by del t there.
that is right. Yes, yeah.
Now again, I at least think that is why we have to sort of do a Lorentz boost plus rotation in order to get psi tilde and chi tilde as decoupled. But
No, no, no.
are those now
No.
scalars?
That is not the reason at all. In fact, we are doing the computation in a non-covalent way. So therefore, uh, there is no issue with combining these terms in this particular fashion. It happens simply because the way the expressions appear here, that you have a sigma 3 and I sigma 2. Okay, it has nothing to do with the fact that the chi and eta are not scalars.
Yes, but in order to allow for a unitary transformation as a change of base.
Yeah. Hello.
Yeah.
I,
So
I couldn't hear actually. Can you repeat? Hello.
When we do a
Hello. Can you hear me?
hello, can you hear me now?
Uh-huh. Now I can hear you now. Yeah.
Yeah, I can hear you. So I was saying that when we it in order to get decouple an equation,
Yeah.
like right now we have something in and chi,
Yeah.
and we are trying to rotate eta and chi to a eta tilde and chi tilde.
That's
The
right.
rotation matrix that we choose depends upon which linear algebra eta and chi are part of.
That is right. Yes.
Yeah, so that they are part of this like a Lorentz algebra where the matrix of rotation is from a Lorentz group, the generator.
Yeah. But that is in the auxiliary space. It is in the sigma 3, sigma 2 space. It's not the real space Lorentz transformation.
Uh, why is that? I mean, even if we weren't writing it as sigma 3 and sigma 2, simply if we taking the previous equation as it is,
As it
we
is. Yeah.
simply want to rotate eta and chi to some eta tilde and chi tilde so that the equations decouple.
Exactly. Yes.
So
Yeah.
the rotation matrix would regardless be the same.
That is right.
I mean, it's intuitively seen by sigma 3 and sigma 2 perhaps,
Yes.
but I'm saying that that rotation matrix is a Lorentz, is part of the generator is part of the Lorentz group. That is because eta and chi are in a part of a linear algebra which undergo Lorentz transformation.
Well, it is not obvious at all why it would happen. By the way, maybe I should clarify one point that the two component formulation that I'm trying to do can be done even for the Schrodinger equation. You can write down Schrodinger equation as also as a two component equation. Okay.
Yeah.
So you can just write down a column vector. One component of the column vector, upper component of the column vector is psi, and the lower component of the column vector is del psi. And you can write down this entire Schrodinger equation in terms of 2 by 2 matrix. Okay. So this is not something which is totally new as far as matrix formulation is concerned. Okay. But that if you try to do that with Schrodinger equation, you do not always, I mean, the Schrodinger equation being parabolic, you do not encounter this situation of having that you need a Lorentz type transformation to diagonalize the form of the matrix. Okay. Whereas in this particular case, you need a Lorentz thing. But this Lorentz transformation is not in real space. This Lorentz transformation is in the auxiliary space, which for which the vectors are sigma 3 and sigma 2. Okay. Even if you don't think of them as sigma 3 and sigma 2 are really convenience, you don't worry about it. You just look at this equation. There's a 2 by 2 matrix, 1 1 minus 1 minus 1, and the other one is just 1 minus 1 diagonally, and you want to ask how you diagonalize this. Okay. The answer to that expression is written in terms of a matrix which is off diagonal 1 1. Okay. Like this. Okay. This answer is independent of whether you write it in terms of sigma 3 or sigma 2. Okay. And what is important here is that, like, if you try to substitute S up there, which is what we will discuss soon, e to the is not a unitary transformation, in fact. Okay. E to the is in fact Hermitian. Okay. So one is not even doing a unitary transformation to go from eta chi to eta tilde chi tilde. Okay.
But at the end, are these eta tilde and chi tilde scalars now? Or are they
No.
still transforming under Lorentz transformation?
No. See, they are not scalars because they contain a component which is del psi by del t, right? So if you do a Lorentz transformation, they are not scalars at all.
Eta and chi contain it, but here, since the matrix of rotation itself is dependent upon P,
Yeah.
so that also changes under Lorentz transformation, right?
Certainly. Yeah. But that
I was thinking that these effects might cancel out or something.
No, because one sector, eta and chi sector, depends on time only, and the transformation sector depends quadratically on momentum. So one piece is linear in time derivative, and the other piece is quadratic in space derivative. They don't cancel so easily, actually.
Okay.
So in fact, there is no space-time Lorentz transformation which would give you this transformation, actually. This is a really auxiliary space transformation. You have created a two-component vector space, and you're doing a rotation, Lorentzian rotation in that space. And in fact, we need to give interpretation to this particular transformation in a moment. Okay, we will do that in fact.
So
okay.
the last equation that we are obtaining is not covariant.
Last equation, which is the
Last as in terms of eta tilde and chi tilde.
Yeah, not yet covariant. In fact, yes. Yeah.
Okay.
Okay. Fine. So where were we? Yeah. So we figured out that this is the equation, and in fact, you can look at this equation is not covariant at all, because there's a del t here, and the expression is written in this particular form. Now you would say that, like, okay, formally it is covariant in the sense that, like, if I had taken del square, I mean E square is equal to P squared plus P squared C squared plus M squared C to the 4, and taken a square root on both sides, this is how this equation would look like. Okay. But I mean, it is one thing to say that, like, E squared would give you E is equal to square root of that quantity with plus minus sign, as a totally different thing to write that in a two component form and claim that this is actually covariant. It is not. Okay. It is not at least explicitly covariant. Okay, but what we are going to do is to actually reinterpret these quantities as a new Klein-Gordon two-component field, okay, or two-component wave function, okay, which I'll call phi tilde. I'll use this tilde for some time, but I have to define a new conjugate phi, at which point I'll just kind of skip this tilde stuff, because I am using tilde for diagonalized eta and chi variables. So I just decided that I'll continue using this tilde on this thing. But as we'll go ahead, you'll see that at some point I'll drop that. Okay. So we define phi tilde to be this eta tilde chi tilde. Is there a question?
Sir,
Yes.
sir, I was asking that our psi is a scalar in Lorentz transformation.
Yeah.
But so eta and psi, eta and chi are no Lorentz are components of a vector because of del t. But how is that coming? I mean, there's also a psi part as well, which is
No,
not
no, no, no,
transforming.
no, no. They are component of a vector in auxiliary space. It's a different space. You know, I don't know how to say this. Uh, the thing is that, like, if you write something in a matrix form, if you have a column vector, then there is a different vector space that you have defined, because you have defined a column vector, right? Each
Okay.
component of the column vector may behave like a scalar, behave like a vector, behave like a fermion, whatever, right? You can just have a column vector containing two fermion, right? A fermion called psi1 and a fermion called psi2, right?
Yeah.
Okay. Then there is a vector space defined because it is a a column vector with two entries. Okay. That space has nothing to do with what happens to the fermions with respect to space-time transformations. Okay.
So they are having a transformation. I mean, not like in space time, but in
Not at all.
sigma 3,
Not
sigma
at
3,
all.
sigma 2, I, and sigma 1.
No, not at all. In fact, I want to rotate eta and chi, and eta and chi rotation is a Lorentz boost. Okay. So it is not it's not T X Y Z Lorentz transformation, but it is a Lorentz transformation in the wave function space. Okay. The wave functions are
Okay.
written in terms of two component form now, and in that column vector I do a Lorentz transformation. Okay. So that is why I was saying that this has nothing to do with the space-time Lorentz transformation. It is not.
Okay.
Okay. So if I had not done this, not written it in a column vector form, then I wouldn't have this Lorentz transformation available at all. Okay. The Lorentz transformation is available simply because I have these two column vectors, and my inner product in this column vector space is indefinite. Okay. Look at this transformation. If I try to diagonalize this matrix, it will be diagonally 1 minus 1, and therefore the inner product is indefinite. Okay.
Okay.
Right. So what we'll do is that we'll write small notation phi tilde for this two component formulation. Okay, and then all the physical observables would be written in terms of bilinears of phi tilde. Okay, this is pretty similar to what are used to doing in, say, in case of non-relativistic Schrodinger equation. Okay, that we would write down observables as integrals of psi star O psi, where O is the operator that we O's expectation value is what we are trying to determine, and so on. Okay, fine. So if you want to try to write down observables like that, okay, then we know that under the change of basis, phi tilde would go to e to the I times s times phi tilde. Okay, fine. That is the kind of transformation phi tilde undergoes. Okay, whereas the observables will transform as e to the is o e to the is inverse, which is same as e to the minus is. Okay, so that is how the observables would transform, because it's a similarity transformation. Okay, but notice that e to the is, where with s defined this way, okay, there's a factor of I and minus I would cancel out, and then you have e to the some real quantity sitting up there. Okay, with this being a Hermitian matrix, this entire expression is actually Hermitian. So e to the is is not a unitary object, but it's a Hermitian object. Okay, so therefore, the invariant bilinears are not of the same type that we had written down for the Schrodinger case. Okay, in the Schrodinger case, if you had done a transformation like this, okay, psi star would have given e to the minus is, and then it would kind of cancel the piece that the transformation of O would have, and therefore this quantity is actually invariant under a transformation of similarity transformation of this kind. Okay, but we will see in a moment that this is not what is going to happen when we write down bilinears in terms of phi tilde. Okay, so let's see. So the right kind of bilinears that we should really write down are bilinears of this kind: phi tilde dagger sigma 3 times O times phi tilde. Okay, and sigma 3 is necessary in this particular case. We will see in a moment why. And the sigma 3 is necessary because e to the is actually a Hermitian operator. Okay, so therefore, if you consider a transformation of phi tilde going to e to the is times phi tilde, then phi tilde dagger is phi tilde dagger times e to the is again. Okay, because this entire object is Hermitian. Okay, fine. So therefore, instead of sigma 3, if you had defined phi dagger, um, phi dagger tilde or phi tilde, then the following thing would happen, that phi tilde would give you e to the is from the right hand side. Okay, and that would cancel with e to the minus is of the operator piece. Okay, and therefore there is no factor on the right hand side. But on the left hand side, you have e to the plus is from the operator under similarity transformation, whereas phi tilde dagger would give you e to the plus is again. So you would end up with e to the 2 times I times s factor sandwiched between phi tilde dagger and O, and no factor between O and phi tilde. Okay, so clearly
Sir,
under similarity transformation, the quantity does not remain invariant. Yes.
sir, in the second point that you have written, the 5 dagger must go to 5 dagger e to the power minus is, I think.
No, no, no. Because exponential e to the is Hermitian. Okay.
Okay.
So therefore,
So,
exponential e to the
so
is dagger is exponential e to the is only.
yeah.
Okay. Fine. So therefore, there is no cancellation if you look at bilinear operators of these kind. Okay, under such transformation, they won't survive. Okay, uh, but remember that S contains sigma 1 in it. Okay, and therefore, if you insert a sigma 3 in the bilinear, then sigma 3 will anti-commute with sigma 1, and it will flip the sign of e to the is to e to the minus is. Okay, so therefore, if you have a phi dagger giving e to the is, if you take it across sigma 3, it will become e to the minus is, and it will cancel e to the plus is of the operator and give you this entire expression to be invariant under such similarity transformations. Okay, fine. Now you may have seen something like this if you have studied Dirac equation. It also has similar structure. If you are not, then as we will study when we will do the Dirac when we'll do the Dirac equation. Okay, but even in Klein-Gordon equation, if you write it in a matrix form, you actually do get your bilinear defined little differently. Okay.
Just aside
Sure.
that in usual Schrodinger equation, we like ourselves stipulate that, right? Oh, the transformation for an operator, this, yeah, this,
This
the
one.
second last point is stipulated this way so as to preserve the norm, so as to preserve the eigenvalues and the
Under no. Similarity transformation is purely mathematical stuff. It has nothing to do with quantum mechanics or Schrodinger equation.
so no, what I was saying, when we know that our basis vector transforms a particular way,
Yeah,
we demand that the operator transform it's in a complementary sort of way so that the expectation value remains the same, and that is how we get this expression psi star O psi.
exactly. But that is a matrix mechanics result. It's just completely matrix algebra result, right? Quantum
Yeah.
mechanics uses it, but quantum mechanics doesn't own that result. It comes completely independent of any physics.
If you could go to the next slide, just
Yeah,
like, couldn't we? I mean, I'm not sure, but now that we know that phi tilde and phi tilde dagger transform this way, that they both produce an exponential iota s,
yeah.
then writing, if we were to treat phi tilde dagger O phi tilde as an operator, then
Hmm.
O necessarily would have to transform in a complementary way that it would produce exponential minus iota s on both sides.
No, not really. The transformations of O are kind of independent of how phi and phi tilde would transform, right? Just take the following thing. Don't forget about phi tilde dagger piece. Just take O times phi tilde, okay? And just multiply by e to the is from the left, okay? That is good enough for you to figure out how O and phi tilde would transform under that transformation, right? Without having without knowing how phi tilde dagger transforms.
I am still under the assumption that O transforms in the unitary case, in the Schrodinger case, in the previous slide,
Yeah.
O transforms in that particular fashion because that exponential iota s is a unitary matrix.
No. Suppose it is a unitary matrix. Okay, you don't need a psi star in Schrodinger representation to figure out how O transforms. Okay, just look at O times psi and multiply by e to the is. Suppose this is a unitary transformation. Multiply by e to the is. Okay, and you can figure out how O transforms versus how psi transforms without even ever knowing how psi star transforms, right?
Yeah, I'm not sure, but I'll
No,
check.
no, certainly, because you can. All you have to do is to decompose identity in terms of U and U dagger, right?
Yes.
That's all you do basically, right? So you don't need a bilinear to determine how O actually transforms. Once you have determined how O transforms, then you can ask how the bilinears could be invariant.
I mean, we are just dictating that under that rotation, the unitary matrix, all vectors shift by exponential iota s.
Yeah, that is
So
true.
even something like O psi would shift like by exponential iota s if you remove the psi star,
Ex- Exactly. Yeah,
and that will give us the transformation for O.
exactly. Without knowing how psi star transformed.
Yeah, but in our new this Lorentzian sort of rotation, this
Yeah,
boost plus rotation,
yeah.
you have to dictate that something like O phi dagger transforms as exponential iota s pi dagger.
Yes. No. See, in this case also, you can determine how O transforms by just saying that e to the is on O phi tilde, okay, is a transformation. And that will tell you that phi tilde transforms this way and O transforms this way without ever, uh, you know, deciding as to how phi tilde dagger would transform. Okay. These statements are independent of how phi tilde Tagore would transform.
So could you please repeat? Your voice got cut.
I said that these two statements, phi tilde transforms this way and O transforms this way, okay, is actually independent of how phi tilde dagger would transform. Okay.
Oh, okay, yeah, I see it now.
Yeah. Okay, so therefore, what kind of bilinears that you can construct depends upon how how invariant bilinears can be constructed. Okay, and what I'm trying to claim is that this is an invariant bilinear and this is not. Okay, the same kind of stuff we'll encounter in Dirac equation also. Certain class of bilinears are not invariant, and some other class of bilinears are invariant. Okay, so let's so let's proceed. And so what we learn is that this factor doesn't get cancelled, but if you insert sigma 3, then because of the anti-commutation between polymatrices, e to the is goes to e to the minus is, and this quantity becomes invariant. Okay, so what we'll do is we'll define the phi bar as a new object, which is a conjugate object to phi tilde, and this phi bar is phi tilde dagger sigma 3. Okay, and in fact this phi bar, if you go back to the original equation, you will realize that the original equation written in terms of phi would be a first order equation in time. Okay, fine. So therefore phi bar is some kind of a canonical conjugate of phi. Okay, this is exactly what we will do when we do Schrodinger, Dirac equation also, that the psi bar would be a canonical conjugate variable simply because your equation itself is first order in time. Okay. Okay, so where am I? Yeah, okay. So the right kind of invariant observables therefore will be a phi bar. Sorry, I should not have put dagger here. Phi bar O phi. Just a sec. Okay, so that is the kind of quantity phi bar O phi. Okay, and this is an interesting representation because in this representation, this comes very close to the kind of quantities that you would write down, say, in the Schrodinger equation. One interesting aspect is that if you are to look for charge density, then charge density in this representation would correspond to O being just 1. Okay, and therefore the charge density is just phi bar phi. That comes pretty close to writing psi star psi in the case of in the case of Schrodinger equation. Okay, and mm, but remember that, like, if uh, this phi bar phi actually has a hidden sigma 3 sitting around there. Okay, although when you write O is equal to 1, it is not immediately visible, it just looks like phi bar phi. Okay, but because sigma 3 is sitting inside it, the upper component has one sign, the lower component has an opposite sign, and therefore we know that the upper component would correspond to the positive charge and the lower component would correspond to negative charge. Okay, of course, we are kind of assuming that one of them is positive. All the correct statement is that the upper and lower component have opposite charge. Who is positive depends upon what is multiplying it. Okay, but yeah, let's say it is this way, that upper component has positive charge, then the lower component would have negative charge. Okay, so this way of formulating the Klein-Gordon equation makes it look uh, very much like the kind of expression that you would have written down uh, in the Schrodinger equation case. Okay, fine. The interesting thing is that instead of just looking at charge density, you can look at the entire current. Okay, so if you look at the current, then you can write down J mu in terms of the operator O, which is sigma mu. Okay, so I have not put any index on operator O because operator O is kind of abstract object, but J mu would require an index, and therefore sigma mu is that operator. And sigma mu is defined in the following way, that sigma 0 is identity. Uh, I really mean a 2 by 2 identity matrix, but maybe I'll have to use some AMS font to get that look like a matrix identity, but that's what it is, and not a number. And the remaining values of mu, that is 1, 2, 3, these are just ordinary Pauli matrices. Okay, uh, so therefore the current that you would write down is phi bar sigma mu phi, whose zeroth component is phi bar sigma 0 phi, but sigma 0 is just identity. Okay. Okay, so this basically gives us a prescription of defining invariant observables, sandwich those observables between phi bar and phi, and not sandwich them between phi dagger and phi. Okay, good. Okay, so, but the thing is that, like, original positive and negative energy states, which are defined in terms of eta and chi, are both required in the process of diagonalization, and both eta tilde and chi tilde are some kind of linear combinations of original eta and chi. Okay, is kind of manifestation of the fact that the system has to be totally effectively Lorentz invariant. Okay, so although the formulation is not manifestly Lorentz invariant, if you put transformations of psi and psi dot into this expression, you can show that the final equation is Lorentz invariant. Okay, so it's like for example, when you do quantum field theory, although most of the simple quantum field theory you wouldn't do anything, you'll try to do it in a Lorentz covariant way all the time, but you may have, I mean, you may want to study, say, quantum field theory involving vector fields, okay, as against, say, scalar or fermion or something. You may want to study theory with vector fields, in which you may want to choose something like a light cone gauge. Light cone gauge has the advantage that it correctly picks up the physical degrees of freedom of the vector field. Okay, then that formulation is not manifestly Lorentz invariant. But every time you do the calculation and you get the answer at the end of the computation, you can show that the result is manifestly Lorentz invariant or Lorentz covariant if you are looking for a Lorentz covariant quantity. Okay, so this setup is pretty much like that. That at no stage you can actually see things, manifestly Lorentz invariant. But if you kind of work through the Lorentz transformation for each component sitting around inside the etas and chi's and so on, you will find that the equation would be Lorentz invariant. Okay, fine.
So,
Yes.
so this eta dagger eta and chi dagger chi are positive and negative charge densities, right?
Eta tilde and chi tilde, is that what you meant?
Because that wouldn't matter because e raised to is not like when we are writing this bilinear, e raised to is not playing any role.
What is not playing any role? I couldn't hear.
Exponential is.
Yes. Yeah.
The operator that is not playing any role. So we can simply write for the charge density operator this bilinear as eta dagger eta and
Yes.
minus chi dagger.
Absolutely. Absolutely. That I completely
Okay.
agree.
Yeah.
Okay. Yeah. So, but only after you write it in this particular form that you realize that the positive energy, positive charge component is just eta dagger eta, and negative one is minus chi dagger chi.
Yeah.
Okay. Fine. Because chi dagger chi would have given you a positive answer, but because of the sigma 3 sitting there, there is a minus sign and it gives you opposite answer to what eta dagger eta would have been. Okay.
Yeah.
Okay, good. Okay, so so this is the statement that you can write down the current in terms of Pauli matrices, and to get the full Lorentz invariance, you need both the pieces together. Okay, fine. Now, to kind of understand this particle and antiparticle characteristics of these fellows, what we will do is that we'll couple this equation to electromagnetic field, and uh, and we kind of try to understand how to solve Klein-Gordon equation when the charged scalar field is coupled to is experiencing some background electromagnetic field. Okay, and the technique for doing that is something which is well known. We have done this in uh, ordinary quantum mechanics also. You replace p vector by p vector minus e times a vector. Okay, so since we are keeping track of c also, we know that it should be e by c times a, and since we are doing covariant formulation, we'll write on p mu going to p mu minus e times a mu by c. Okay, this change is what is called the minimal coupling of gauge fields uh, to the charged particle. Okay, and I'm sure you must have studied that the minimal coupling is kind of forced upon us when one tries to say that if you look at some local transformation of the wave function, then p mu acting on the local transformation of the wave function is not invariant, but p mu minus e times a mu uh, acting on local transformation of the wave function is covariant. Okay, so that is one of the reasons why this minimal coupling is also called a covariant derivative. Okay. Okay. So so what happens in this particular case is that when you change p mu to p mu minus a mu, it also changes p0 to p0 minus a0. Okay. So you have this additional factor e times a0 uh, in the uh, in the Klein-Gordon equation. We know that A0 is the Coulomb potential, and when we tried to solve Schrodinger equation, it was part of the potential that we had to put in, besides doing this kind of modification for the spatial part of the Schrodinger equation. But Klein-Gordon equation involves second time order time derivative, and therefore you get E times A0 uh, uh, in kind of squared form in some sense. Okay, although if you write it in the matrix form, then it is okay, then it still comes as a linear thing because our equation is linear in time. Okay, so you replace I h bar del t minus e times a0 here. Okay. Fine. Okay, now so notice one important thing that that in the two component representation A0, remember, maybe I just step back, the operators that one is trying to use are something like this. You have a sigma 0 to be identity and sigma to be a polymatrices. Okay, so A0, or you could even go back to the original equation also, this doesn't have any matrix multiplying it. Okay, so when you replace IH bar del t by IH bar del t minus E times A0, then E times A0 has an identity matrix sitting with it. Okay, so that is the kind of statement that I want to make, that in the two component representation, A0 is actually multiplied by 1, whereas MC squared is multiplied by sigma 3. Okay, so that was maybe we'll have to go all the way back to look at this expression, that MC squared is multiplied by sigma 3, whereas A0 is sitting on this side, which is multiplied by the identity matrix. Okay.
So, but we are operating this p mu minus I a mu on psi, not eta tilde and chi tilde, right?
No.
So, and
Why?
eta tilde
No,
and chi
why?
tilde already contain derivatives of psi.
No, I'm not acting them on eta tilde and chi tilde. I'm acting them on eta and chi. Eta tilde and chi tilde is just a trick to kind of diagonalize
Let's say eta and chi,
yeah,
eta
yeah,
and chi, but
yeah.
they in principle they should be operated on psi, right?
No, there is nothing. I mean, this is the equivalent formulation. No, there is nobody who can tell
But
which
the
formulation to use,
point
right?
is eta and chi contain derivatives of time, right?
Uh,
So if you
see if the
eta and chi
description,
in definition they,
it doesn't matter. If this description is equivalent, then I can use this description equally well. Okay, there is nothing in a quantization procedure which tells you that I should always function with the original psi variable. If this description is equivalent and equally good, I could use this representation also. I mean, let's put it little differently. Imagine if somebody had written down this equation in this form first, and later on realized that like, oh, I don't have to write it in a matrix form, I could write it in a scalar form, and it is just a second order differential equation. Okay, how would you decide which one you want to I mean, in which case you want to replace P by minimal coupling case? Okay, and the answer is any one of them. Okay, it doesn't matter which one you use. Okay, and if your physical answers are going to be different, then the two representations are not even equivalent. Okay, so all the physical observables should be same. It doesn't matter if you are going to claim that the matrix representation and the scalar representation of the equation is identical, all of them should give you the same answer. Okay.
No, all I'm saying is in the definition of eta and chi, we should like when we are writing eta in terms of psi,
Yeah.
we should even there we should change del del t to del del t minus I a0.
No, not necessarily. In this definition?
Uh, uh, the slides are still changing. Yeah, here.
Yeah. Well, not
It should
necessary.
be IH cross. Why is that? I don't see it.
Because what I'm claiming is the following, that what I'm saying is that like the two component formulation that I'm trying to give, okay, is equivalent to the single component formulation. Okay. Suppose I gave you this formulation of the Klein-Gordon equation first. Okay. Remember
Yeah, that I understand, but the definition I think should change.
no. This is simply because you have that prejudice that I brought you from psi to eta and chi. Okay. But if I started off with eta and chi to start with, saying that like, okay,
So we
I know
can't hear you, I think.
no, okay, let me repeat. I was saying that like this is happening because we started with a prejudice that psi is the original variable and eta and chi are derived variables. Can you hear me?
Yeah.
Okay, but one could have just started off directly with eta and chi and this equation, these two equations. Okay.
Excuse me, but sir, haven't we just formulated this equivalence for a free particle picture, not under a potential?
Yeah, that is right.
As soon as we add an electromagnetic field, we have to like sort of reformulate eta and chi in terms of psi by using a covariant sort of derivative for time and
Yeah.
space.
So that's what I'm doing, right? I'm replacing del t by covariant derivative and grad by covariant derivative.
No, but starting from the definition of eta and chi, because eta
No,
itself contains a time derivative.
That is the point. The question is that like, what is the definition? What is the original variable, right? I told you that this is the way the original variables relate to eta and chi. But what if eta and chi are original variables and psi is a derived quantity, right?
So in the Klein-Gordon equation, if we
Yeah.
were to add a potential,
Yeah.
we would still do this only, that replace p mu by p mu minus this a
Yeah.
mu.
But like, suppose I told you that Klein-Gordon equation is in this form. Okay.
But this equivalence, at least it's only visible for a free particle case.
That is
For
right.
explicitly showing it for an additional potential a mu,
Yeah. So
we
in
need to
quantum,
replace p mu
yeah.
by p mu minus a mu everywhere.
Yeah, but in quantum theory, there is no guidance which tells you what is the more fundamental way of doing it. Okay.
No, we aren't arguing about fundamental equation being Klein-Gordon equation. It's just that in order to draw an equivalence,
Yeah.
the derivatives must be replaced everywhere, even in defining eta and chi in terms of psi. After all, given one equation, I should be able to retrieve the other equation, right?
That is right.
Given the relations between
Yeah.
eta, chi, and
So
psi.
it will be retrieved automatically. right? Because it is in the component form, right? You have this A0 acting on this fellow, and eta contains chi inside it, and therefore whenever you substitute chi derivative inside that, it will take A0 once again. Okay, so if your worry is that what happened to A0 squared term, it will come automatically.
Using this, when we try to rewrite an equation in psi, it should be the same equation that we would have
Of course,
gotten using
of course,
original
of
time
course,
coordinate equation.
of course. Otherwise, physics cannot be the same, no? See, if I'm doing a different equation and if I do the computation using a different equation, okay, let me put it differently. Suppose I take a derivative of eta, okay, then that derivative of, okay, let me go back. Let's look at this equation. Suppose I take time derivative of eta, that would involve a time derivative of chi,
Yes.
right? Now I have a covariant, suppose I replace this by a covariant derivative of with respect to time, okay? Then that would involve a covariant derivative with respect to time of chi also, okay? So it will automatically give you a second component of A0, okay? So by the time you go to the Klein-Gordon equation, okay, you automatically get two copies, double copy of the A0.
Yeah, that much. This equation and dealing with it in terms of covariant derivative is fine. But suppose I want to retrieve the Klein-Gordon equation under a potential using this equation. So
Yeah, if it works with
apart
covariant
from,
derivative, it will produce the equation correctly, no?
yeah, but when we are substituting eta and chi in terms of psi,
Yeah,
like if you could go a little above, that psi by 2 plus and
yeah,
minus,
yeah.
no, the definition of eta and chi. Yeah, this psi by 2 plus and minus, here also we need to put an A0
No, you
when
don't
we are
have to
trying
do
to
that.
retrieve
That
the
is,
Klein-Gordon equation.
yeah,
No?
you don't have to do that because once you move to eta and chi, you have forgotten the right hand side of this piece. You just write down this equation, you replace del t by covariant derivative, okay, and then covariant derivative both on eta and chi implies that A0 appears twice, okay. Is it making sense?
So in this slide, only the second line where you have written but iota h cross something.
Yeah.
Uh, in the Klein-Gordon equation, we do not directly substitute del psi by del t in the no, in the potential case.
Yes.
If we were to, let's say, do this entire thing under a potential,
Yeah.
and in Klein-Gordon, instead of having del by del t and del by del psi, del by del x, we had this del by,
No, no,
like
but
in
like,
terms of a0 and a.
let me put it this way, that suppose I had told you that this is the problem that you want to solve, okay, and couple this to electromagnetic field, okay, what would you do?
Yeah, this equation itself is fine, but the form for eta and chi in terms of psi has to be sort of modified.
But I mean, okay, but I don't care, no, I am going to just write it in terms of eta and chi and finally derive what is the equation satisfied by psi, right?
Yeah,
So if,
that would be fine.
exactly, so that's all I'm trying to say, okay. So the A0 modification that you may want to do in this definition is not something which I need to do right now. Eta and chi will automatically take care of that, if that is what is the worry.
Yeah. If we want to forget the Klein-Gordon equation and work with this sort of two-component equation, that
Yeah,
is perfectly all right.
yeah. And if the worry is that like why am I not converting this into covariant derivative? Well, I would be, but I don't want to do that. I just want to work with eta and chi would automatically take care of covariance of this equation. Okay, if that was the question.
Yeah.
Oh, okay,
Okay.
yeah. So I don't have to worry about redefining that quantity. I just work with eta and chi automatically
Yeah.
knows that this term has to be a covariant time derivative and not the ordinary time derivative. And
Yeah.
that will
Yeah.
automatically
My only question was if person A is working with psi and
yeah,
the person B is working with eta and chi,
yeah,
and they want to relate eta and chi with psi, then they have to replace uh, time derivative with covariant derivative
that is right.
everywhere.
That is right. But if you do
Yeah.
time derivative replacement to covariant derivative here in this equation, here as well as
Yeah.
covariant
That would be
derivative
fine.
here, that itself would take care of the other definition. you don't need to do anything more.
Okay. Yeah.
Okay, because
Hmm.
when you take a covariant derivative here and a covariant derivative here, when you act the covariant derivative once again, then that derivative is acting on chi here. You plug that fellow up from this equation and put it back in, and you'll get the Klein-Gordon equation with the with covariant time derivative squared
Hmm.
automatically. Okay, so without even worrying about what is the modification that you need to do, eta and chi knows how the relation between eta and chi to psi modifies when it couples to an external field. Okay, and
Yeah.
that is the
Matlab,
equivalence
all
of,
the
yeah, please.
all the observables will be the same in both the formalism.
Yes, yes, exactly. All the observables
Okay.
will be the same. So in that sense, it's an equivalent formulation. And then if you really want to go back and ask, you know, how do I relate these quantities? This would be replaced by covariant derivative. But you don't even need to do that. That is my statement. Okay, you don't even need to worry. The chi and eta automatically knows how to bring out a psi out of the two component formulation.
Okay. Okay.
Okay. Yeah. So I think we are almost out, yeah, close to the end of the class. So what we'll do is that, yeah, sorry, I have to go further down. What we'll do is that we'll set up this problem in two component formulation. Okay. And try to see how we would go about solving it. So, but I just wanted to make a comment here that in the two component formulation, A0 is multiplied by 1 and MC squared is multiplied by sigma 3. So, as, so what we find is that like the Coulomb correction, which is generated by this A0 piece, because that is a Coulomb potential, okay, this correction is opposite for positive energy and negative energy states, okay. Right, so that is a kind of consistency check for two component formulation, that you write it in a matrix form and they would give opposite corrections for uh, positive and negative energy states. Okay, now this is not immediately obvious you because of the identity fellow, but because psi and chi have a sigma 3 sitting around with a negative, uh, I mean, because they carry opposite charges, the corrections, these are factor E times A naught. So although you have an identity matrix, E for eta and E for chi are opposite. Okay, and therefore they do give opposite corrections to this. Okay, which is consistent with our understanding of the particle and antiparticle degrees of freedom. For a given Coulomb potential, they would have opposite corrections. Okay, so what we'll do is that we'll try to kind of set up this problem, and we'll try, and we want to basically solve this problem, because as I said in the earlier class, that Schrodinger did not get the answer right when he compared his results uh, with the hydrogen atom spectrum. So we'll try to see, we'll derive this result and we'll see where it does not agree. Okay, and then we'll see how Sommerfield's result agreed and why it actually should not have agreed, but it did. Okay, so that is probably in the next class. So our next class is on Monday, right? Hello?
Yes, yes,
Yeah,
on Monday.
okay. So,
So
So,
this
one question: like,
yeah,
who started giving this kinds of formulation? Like, it was not Schrodinger, right?
this
Like, who
formulation,
started
two component
using
formula.
eta and chi?
No,
Yeah.
Schrodinger did not use the two component formulation. In fact, he used the scalar formulation.
Okay.
Yeah. So this two component formulation is basically uh, comes from the Schrodinger equation itself, because you can write down Schrodinger equation as a two component equation. So simply because you have a second space derivative, so you can define the first component to be psi, second component to be derivative with respect to x or nabla on psi or something. And this is a usual thing that one does in differential equation. In fact, this formulation is called the Fuchsian formulation for the differential equation. So given that you can do it for this, for a parabolic equation, it should be possible to do it for hyperbolic equation. So Klein-Gordon is a natural hyperbolic equation for which one could do this formulation. Okay, and This is what is called the Fuchsian formulation of these differential equations. Okay.
Okay.
So that in fact predates all quantum mechanics. It was like late 19th century, early 20th century formulation. This thing. But for some reason, it was not used, except of course Dirac, who realized that uh, that he needs to use a matrix formulation to get the first order equation. Uh, but I don't think Dirac, at least Dirac's paper doesn't refer to Fuchsian formulation of differential equations. So maybe he came up with this idea completely independently.
So
Okay. Yeah. Yes.
that the charge of the antiparticle, the electronic charge,
Yeah.
I mean the Coulomb charge,
Yeah.
is opposite of the particle. Is it is it something that we put explicitly, or does it come out on its own?
Well, uh, in some sense, it should come out on its own, simply because all quantum numbers have to be opposite for a part for that object have to be an antiparticle, right? Because uh, the particle-antiparticle pair is supposed to be created out of vacuum, uh, purely based on availability of the energy. So, barring the energy, or barring the rest mass of the particles, okay, which of course have to be positive for both of them, all other quantum numbers have to be opposite, such that total quantum number of the pair is proportional to the vacuum quantum numbers. Okay.
But Coulomb charge isn't a quantum number, right?
It is, no?
I mean, we don't treat it as one, at least not in these equations.
No, you do. You do, right? There is a conserved current corresponding to that. And that charge is not only classically conserved, but even in quantum theory it is conserved, right? And it's a measurable thing, so it's a observable in quantum theory, right?
Okay.
Every observable is a quantum number in quantum theory, right?
Yeah, but what's the observable for Coulomb charge?
What is observable means charge itself is an observable, no?
Yeah, but in operator form or anything, I mean, we just feed in this Coulomb charge as a factor sort of a thing.
Yeah.
But I mean, I don't think we directly talk about measuring charge.
I mean, where? What do you mean by
Quantum
we?
mechanics in general, I mean, I don't think we treat charge as an observable.
No, we do, of course. In non-relativistic quantum mechanics, no. But relativistic quantum mechanics, yes. In non-relativistic quantum mechanics, you don't define that simply because you define a quantum mechanics problem with a positively charged or negatively charged particle, and then from the beginning of the problem till the end of the problem, you have only one particle, right?
Yeah,
Okay,
that's what I'm saying.
and
It's
its charge
simply
its
something you
charges.
feed explicitly.
Yeah, exactly. But not in non-relative, not in the relativistic case, because in the relativistic case you may have a fixed charge sector, but the fixed charge sector can contain any number of particle-antiparticle pair plus the fixed charge, right?
But
Okay.
so far in only the Klein-Gordon equation in whatever component form,
Yeah.
we are simply replacing still P mu by minus E, A mu by C. Here
Yeah.
we are explicitly feeding E,
Yes. Yeah.
and we don't yet know whether it's a positive charge or a negative charge.
Absolutely. Yeah.
So what will tell us whether we are feeding a positive charge or negative charge?
Well, mathematically nothing, right? But experimentally, of course, you know how to determine, right? I mean, you just apply a magnetic field and you would know which way it turns.
Yeah, so that's what I'm saying. That the antiparticle turns the other way around or something like that. That
Yes. Yeah.
comes
Exactly.
through the equation.
Exactly. Yes.
No. Will it or will it not?
It will.
It will.
You apply magnetic field, positive charge particle move one way, negative charge particle move the other way. So antiparticle would move the opposite way, in fact.
Yeah, but will that be apparent without knowing whether the sign of E is positive or negative?
No, it is independent of sign of E being positive or negative. It is that the sign of charge for the particle versus antiparticle are opposite. That's all. So particle could be negatively charged, antiparticle positively charged, doesn't matter as long as they are opposite. In the magnetic field, particle will move one way, and in one circle, say right-handed circle, antiparticle will move in left-handed circle for the same magnetic field. Okay, if particle moves in the kind of clockwise fashion, the antiparticle would move in anti-clockwise, or vice versa. Whether the particle has positive charge and antiparticle has negative charge is purely a convention. I mean, we say electron has negative charge is complete convention. Okay.
Okay.
Because it doesn't matter. I mean, you call electron has positive charge and proton has negative charge, nothing would go wrong. Everything would work out actually.
Yeah.
Okay. But what is important is that the particle and antiparticle has to have opposite charges and all other quantum numbers opposite actually. Like if it carries any internal quantum numbers, if it I mean, if you produce it from the vacuum, then they should have, if they carry spin, then those spins should also be opposite. They should the spin projections have to be such that the total spin of the system should be zero. Okay, and that's why it is in some sense what in quantum information you would call an entangled state. Because if you detect the spin of the particle, you immediately know what is the spin of the antiparticle if you have created it from the vacuum. Okay. But if you have created it in the presence of, say, an electric field, then you won't be able to guess that, simply because electric field is already kind of producing a vector. And with respect to that, what kind of pair is created, okay, whether it is a spin zero component, I mean pair, or spin one pair, is not so easy to determine. Okay. So in that sense, uh, anything which is created as a pair created in a vacuum, the antiparticle would have all opposite quantum numbers except energy, except mass.
Okay.
Any other question? Okay, so can we close now?
Sir, could you suggest
Okay.
a book where we can find these things?
For this, I'll have to check. This is just a actually differential equation formulation. So I don't know where it is. This thing.
Bjorken and Drell has this.
Bjorken and Trail has this kind of stuff.
Yeah, first two chapters is pretty much the same thing.
Klein Gordon written into component form.
Yeah,
Oh, okay.
even in the first chapter it has this.
Okay, okay. So yeah, so there it is. Bjorken and Trail would have it. But I can check if there is anybody else. Okay.
Yes.
Okay then.